All right, so here we go. We're talking about second order integrated rate law now. All right. Now, for a second order integrated rate law, there are a variety of different rate laws which are integrated to this value, which we'll talk about, to this expression, which we'll talk about in a second. But your rate can be a to the second order, or a to the 1, b to the 1, or a to the second, b to the 0, right? A handful of ways that you can get second order relationships, second order dependence on your reactants. All right. And the integrated equation can come in this form here when you have one one reactant that you're interested in its dependence in the first or the second order. Okay? And this is going to be concentration of A at some given time, this time over here, and this is going to be the concentration initial again. And what this basically is telling us here is, again, we have a linear relationship. We have our slope times our time, m over m x, y equals mx plus b if we move this over to there. So this 1 over y naught is our y-intercept, and this 1 over at, concentration of A at any given time point, is our y-axis. Or in other words, for a second order reaction, the plot 1 over the concentration of A versus time will be a linear relationship. Okay? Now, this linear relationship doesn't go from top to bottom, because if I'm saying 1 over A, then you start off with a higher concentration that will make a larger value or a smaller value on this plot of 1 over A. So 1 over A versus time will be a linear relationship if you have a second order reaction. All right, so we can use this integrated rate law to solve these problems here. All right. The rate constant for the second order reaction, we're told it's a second order reaction, is given here. That's the K. What is the original amount present after 2 hours? What's the original amount if after 2 hours this is the amount that's available? Well, what's the equation for the second order integrated rate law?
I didn't write it down fast enough.
Okay. You can look it up on Google, right? That's good. However, one thing that we do want to remember is that for a second order reaction, if I make a plot here, here's a second order reaction, and I plot the concentration of A versus time, do I get a linear relationship?
No, you only get a linear relationship, concentration of A versus time, for a zero order.
That's right. And for the natural log of A, that gives us a linear relationship. How do I get a linear relationship if I plot it versus time for a second order reaction?
Oh, it's 1 over.
That's right, 1 over A. So if I remember this, if I remember that plot there, then I can recognize that y equals mx plus b here is going to be in y. That's my 1 over A. And this is 1 over A at any given time point, right? Because we're getting A at all these different time points. The B, y equals mx, I can see as time. X, I can see as time, right? And B is going to be the 1 over A again, but at time equals 0, right here, right? That's the y-axis. So it's 1 over A for time equals 0, right? And that slope is what? Do you remember?
Oh, that's the rate.
That's right. That's the rate. So look, I've regurgitated it because I remembered that 1 over A versus time is linear for second order reactions. Okay? So that's the kind of thing we want to be able to do. Now, if I put in what values are provided for us here from this equation?
We got K, 5.3 times 10 to the minus 5.
5.3 times 10 to the minus 5.
after 2 hours, so we got T.
Very good. Now, there's something wrong there, though, huh?
Oh, yeah, it has to be T 2 times 3600 to get it in seconds.
Very good, because our rate constant was in seconds. Therefore, 2 times 3600 will give us in seconds, so 7200 here. Squeeze in a couple of digits there. 7200. What else have we provided?
The original amount is what they're after. 0.35 is available after 2 hours, so 0.35 will be the one on the X.
Or on the left, you mean?
Yeah.
0.35 molar. Okay, and then we're going to solve for our X here, right?
Yep.
So 3.5, let's see, we got the math up here. 3.5 times 10 to the minus 5 times 7,200, right? And then we're going to subtract 1 over 0.35 from that and get 1 over this. And I'll bet you can do the math. If it's confusing for you, push pause and work through it until you get it. But that is how we get our concentration at initial for this second order reaction under the conditions that they provided. A second order half-life. A second order half-life, we're not going to talk much about this, but there's only one type of order that has a fixed half-life. Do you remember what that is?
That was the first order.
That's right, 0 order. Each half-life will be different, and the same is true for a second order half-life. Each half-life will be different. In fact, the equation for the second order half-life has a dependence on the concentration of A. All right, so if we're given the rate constant for a second order reaction, here it is. What's the half-life if we start with the concentration of 5? Well, we can use this equation again, which is the equation for the second order reactant half-life. And you know, if I were you, to kind of simplify your life when you went into any exam where you thought there would be questions about kinetics associated with zero first or second order integrated rate laws, I would just write down all the equations and the half-lives, become familiar with them, you know, refresh myself at the beginning, right? But we can just plug and chug here and get ourselves a half-life in the units that they're after. All right, so we just answered this question. Let's see how you can, if you folks at home heard the answer, try to answer this, and then we'll ask you, Fred.
Okay, you guys had time. Here we go. The answer is first.
Oh, good job. That was fast. Which order has a half-life that is independent of the original amount? That's the first order, right? 0 order half-life changes depending on where you start with, and so does the second order, but first order does not. Very good. All right, here we go. 0.1 molar solution of antidepressant decays to a toxic chemical as a second order process. Here's our rate law. What quantity of the material is present after 90 days?
Can't we just plug everything in?
Well, this is a good practice. Let's see if you can do it. Plug everything in, push pause, plug everything in, see if you can get the right answer. All right. Make sure you worked on it. Did you get it?
I did. I got C.
All right. Very good. So what did you plug into AT?
That was the initial point. Oh, no, sorry. That was what we were after.
Okay. So A0?
That was 0.1.
K?
That's 2.3 times 10 to the minus 3.
And T?
That was 90 days, but I multiplied by 100, or 24, sorry, because the rate constant was in hours.
All right. Excellent job. Okay, now we're going to kind of talk a little bit about, well, actually, this is a good place to stop. Next time.
Oh, man, looked like good pictures.
You'll get it next time.